All right, so this is lesson 19. So what we're going to do is we're going to continue on our trek to finding different ways of determining intersections. And what we're going to deal with today is the intersection of two planes. Okay, so I'll give you a minute or two to just take two pieces of paper or two pieces of cardboard if you have, and see if you can figure out all the possible scenarios that can occur when you're intersecting two planes. So the only thing I'll remind you of is that when you're using, say, a sheet of paper to represent the plane, it's only representing part of the plane, that it's, the plane's actually extending in all directions. Okay, so take a minute to try to come up with all the possible scenarios, and then we'll come back and take a look at that. All right, so we're back. So let's take a look at what we have here. If we take two planes, so what are the different possibilities? So who'd like to give me one of the possibilities here when I'm working with two planes? Okay, so parallel. Now, if they're parallel, I think there's more than one possibility. So what happens? What are two things that can happen? So I can definitely have, two planes that are parallel. And I guess they're parallel and distinct. It looks like they're never going to touch each other. So even if we extend these to infinity in either direction, okay, we're not going to have any points of intersection. But then somebody else is suggesting, well, wait a minute, what if the two equations actually represent the same plane? Okay, so this will unfreeze in a second, hopefully. There we go. So in fact, the two planes are indeed the same plane. So there's infinitely many points of intersection, and essentially it's just all the points on the plane. Okay, so I think that covers all the scenarios where the planes are parallel. So what happens when the planes are not parallel? Okay, can you have a point of intersection? Well, yeah, we'll get to that later on, but what about a point of intersection? What do you mean, no? Why can't I see? Look here, I got a point of intersection. What's going on here? Why is this not valid? It's, has to do with what I said earlier. I'm just taking part of the plane, but we have to remember that, if I do it this way, that this plane extends to infinity. So eventually there's going to be much more intersection. So the only other option, as soon as the planes are not parallel, they intersect in a line. And we can see that here, that they intersect in a line. Okay. So we're seeing our first possible intersection, okay, where intersecting at a point is not even a possibility. Okay, so we know that when we're looking for our answer, we're either looking for them to be the same, which I think we probably have an idea as to how we could tell if two planes are exactly the same, when they're parallel and distinct, and then otherwise we're looking for the equation of a line. Okay, so if we review, got a little diagram here to review the three possibilities. Okay, and I'm just going to make this a little smaller. There we go. So in this case here, where the planes are not parallel, you automatically have a line of intersection. So there's infinitely many points of intersection. And so you're going to have to look for the equation of a line. But what I want to talk about, and this is similar to what we did at the end of the last lesson, where we realized that when we were looking at a plane and a line, you could figure out fairly easily whether the line and the plane were, first of all, parallel to each other, and whether it was parallel and distinct or parallel with the line on the plane. So how could we do the same thing here? So when we're talking about parallel planes, what can we use to show that two planes are parallel? Who'd like to give us, so now we're sort of talking about number 2 here, where they're saying, how could you usually determine whether two planes are parallel and distinct or coincident? So first of all, how do we determine if two planes are parallel? What would be the easiest way to determine that two planes are parallel?
If the direction vectors are related by a scalar multiple.
Now, are you talking about the direction vectors? because the direction vectors get to be a
the
little...
direction vectors in the equation of the plane are the same.
See, the problem with working with the direction vectors is that here I could be having these two direction vectors defining that plane, and on the other plane I could have these two direction vectors, and it's not, you can show that they are parallel to each other, but that actually takes quite a bit of work. That is not something that is easy to show. Whereas I think we have an alternative, which is much, much easier than working with the direction vectors. Because you'd essentially have to show that each of these two vectors can be written as a combination of the other two. I think we've got something much, much easier. And the idea there is to work with the normal vector, okay? That if these two planes are parallel, then they're normal vectors, because remember, how did we determine the angle between two planes? We looked at the normal vectors. That if these two planes are parallel, then their normal vectors are also going to be parallel. So number one, that tells us that we probably want to try to work as much as possible with the Cartesian equation of a plane, because in the Cartesian equation of a plane, we can see straight out the normal vectors. And what's nice about that is it's very easy to tell if two vectors are parallel to each other, if they differ by if they differ by a scalar multiple. So same thing here. If this represents the normal vector to plane 1 and this represents the normal vector to plane 2, then the normal vectors would have to be parallel. Okay? So we'll use that as our starting point. Okay? That if you have two planes that are parallel, okay, their normal vectors will be either equal, or at the very least, they'll just be scalar multiples of each other. Okay, so let's take a look at an example. Let's say I have x plus 2y plus 3z plus 4 equals 0. So I know that this plane, whatever I put afterwards, these two planes have to be parallel, because 1, 2, 3 and 2, 4, 6 differ by scalar multiple. And here, if I have negative 3x minus 6y minus 9z, okay, these three planes are all parallel to each other because the normal vectors are all scalar multiples of each other, okay? So what's going to determine whether they're parallel and distinct or whether they're coincident? So who can tell me what's going to help us determine the distinction between these two scenarios? It's going to be the d value, okay? And that was the nice thing about the Cartesian equation of a plane, is that any two people finding it via any two methods should in the end be able to write it as the same equation. Because here, if I have plus 8 equals 0, and I simplify this by dividing both sides by 2, I get exactly the first equation. So in other words, not only are the a, b, and c values different by the same scalar multiple, so are the d values. So here we have d2 is equal to 2d1. So not only are the normal vectors parallel to each other, but because the d values differ by the same constant, these two represent the same plane. Whereas here, if I have plus 12, what can you tell me about the first plane and the third plane? What is the relationship between the first plane and the third plane? Yeah, they're going to be parallel and distinct, because I look at the normal vectors, and -3, -6, -9 is a scalar multiple of the normal vector of the first plane. So they're definitely parallel, okay? But d3 is not equal to -3 times d1. Because here, what is the scalar multiple between the normal vectors? It's -3 but that's not the case for the d values. So this one here is going to be parallel and distinct. Okay, so the second you're given a question that involves the intersection of two planes, the first thing you should be looking at are the two normals, and are they parallel? If they are, determine if the d values differ by the same scalar multiple. Okay, and if they do, coincident. If they don't, parallel and distinct. All right, any questions on this so far? All right, so if there's no questions, let's start taking a look at a few examples. Okay, so what did I say here? I look at my first normal vector, and I see that, n1 is 2, negative 2, 5, and I have that n2 is equal to 2, 1, negative 4. And what can I say immediately just by looking at this? I don't even need to do any work. What can I say about these two vectors? Yeah, they're not parallel. Okay, so they're not parallel, which means I know I'm going to have a line of intersection. Okay, so this could have been easily solved with very little work had they been parallel, so they're not. So now we have to think about how are we going to deal with the scenarios where the two planes are not parallel. Okay, so as we've sort of seen here, we have this scenario where we have systems of equations, but not the systems of equations that we're used to. When we were looking at the equation of two lines, we had three equations with only two unknowns. Here, I have two equations, but with three unknowns. So clearly there's going to be some differences as to how this plays itself out, which we should expect it to be a little different. But can we recycle any old tools that might be useful here? Because so far we've seen that in each of these cases where it comes down to solving a system of equation, okay, so we could equate the two, in other words, do a substitution, okay, whether it's equating them or not, okay. I would say just equating them because they're both equal to 0 doesn't really help that much, because you just still end up with three variables. But okay, somebody says elimination. Okay, would substitution be a reasonable thing to do here? Can you see something that might encourage you to do substitution? Okay, so here you're talking about elimination. What about substitution? Can you see why, if you were to use substitution?
There's only one y in the second.
There you go. But then my next question is, well, what if I replace this by 7? All of a sudden, substitution doesn't seem quite so useful. So you certainly could use substitution, but I think, as I usually suggest when it's even a regular two equations and two unknowns, as soon as I put some other, some other coefficient in front of here, kind of loses that. Okay, so I think I'm going to go with the elimination. Okay, so here somebody suggested we do the x's, so let's do equation 1 minus equation 2. Okay, and let's see what happens. Okay, so I'll actually write it out. 2x minus 2y plus 5z plus 10 equals 0. And then minus, and equation 2 is 2x plus y minus 4z plus 7 equals, whoops, not what I want to do, equals 0. Okay, so as people suggested, x's cancel out. So what do we have? Negative 2 minus 1, negative 3y, 5 plus 4, so plus 9z, 10 minus 7 plus 3 equals 0. And what we have here is a different scenario than we're used to, because normally in the past, when you did your elimination, you could actually solve for one of the variables. But who can tell me why I don't really expect to be able to solve a specific value for one of these variables. Why is that not surprising? Can somebody explain to me why I shouldn't be expecting to solve, y equals 7 or something like that? How many solutions are we expecting to find? There you go. Is we know that we're expecting infinitely many solutions, okay? So what we can do, I think we can do something. Any suggestions as what we can do with this equation? I can't solve for y or z explicitly as a single number, but what am I able to do? Any suggestions? Yeah, is you can write one variable in terms of the other. That's at least pretty good. It's not as nice as finding an exact value, but at least you can write one in terms of the other. So I hope we're all going to agree that I'm going to isolate y, because that's going to give me a nicer scenario. If I isolate z, I end up having to work with a fraction. So if at all possible, I can avoid working with fractions. I try. If I can't, I can't. Not the end of the world. But here, this is much nicer. So this is just going to give us 3z plus 1. Okay. So at least what I've managed to do is to write one variable in terms of the other. Okay, where am I going next? Who's going to tell me where I should go next? Let's make some suggestions here. Yeah, plug it in where? What do you mean by plug in? Be a little more, okay, there you go, is substitute this back into one of the original equations, okay, like you would have done in the past. So I guess I'm going to choose equation 2 because, it's a little simpler. I have only y there, as we said before, as opposed to 2y. So let me take equation 2, okay, and 2x plus, now instead of y, I'm going to replace that by 3z plus 1 minus 4z plus 7 equals 0. And now, what do you think I'm going to do with this x and z? Who's going to suggest what might be a reasonable thing to try here? So I don't know if I'm sure, I don't know if I understand what you mean by equate them. Make one equal to the other. Okay, I'm going to go out of the, okay, so I think what you mean is solve for one in terms of the other. Okay, and that makes sense. But hey, since I already wrote y in terms of z, what I'm going to do is I'm going to try to write x in terms of z. So at least there's a commonality here. Okay, so let's do that. So here, what do we have? We have 3 minus 4. So we've got minus z. And then here we have 1 plus 7 is 8, plus 8 is equal to 0. Okay, and so now, okay, let me just check my algebra here. 2, okay, 3 minus 4, negative 1. 1 plus 7 is 8. That looks good. Okay, and now let me solve for x in terms of z. So z minus 8. So x is equal to 1/2 z minus 4. Now, you might be thinking, well, wait a minute, wouldn't it have been nicer to solve for z in terms of x? Now, I wouldn't have had this fraction. But there's a reason why I'm specifically writing both of these components in terms of the same one, okay? Because when I look at this here, y is equal to 3z plus 1. X is equal to 1/2 z minus 4. Does that kind of look familiar, where you're writing components in terms of another variable? Does that seem familiar to you? And maybe think about what our solution should look like. Does this not look familiar, where we write components in terms of another variable? And very good. This really looks a lot like parametric form, where I write the x component in terms of some variable. I write the y component in terms of that same variable, okay? But normally we put it in terms of t. So any ideas here? Because, you know, I pick any Z value, I can get some X and Y value. But wait a minute, listen to what I just said. If I pick any Z value that I want, I can produce an X value and a Y value. So what we do is we just let Z be equal to our parameter. And so now I can write this as X is equal to 1/2 t minus 4, because I let Z be equal to t. Y can just be written as 3t plus 1, and then Z is equal to t. And I let t be any number I like. And lo and behold, what do these set of equations represent? There you go. There's your equation of the line. Okay? Now, if you want, you can even take this and write it in vector form if you like. Okay? Not something I would expect you to do unless I ask you to. So what would be the point here? Which point is on the line? Where would I look for a point on the line? So remember, what we need is we need a point plus t times my direction vector. So give me either the point or the direction vector first. Take your pick. It's written slightly 0. Okay, so yeah, I don't even think I need to make t equal to 0. Remember, the point is just given by the constant terms in these equations. -4, 1, well, there's no constant term, so 0. So Andrea, it's what you were saying, but I don't even have to think of it this way. I should just be able to look and see that -4, 1, 0 is a point. And let's remember what gives us our direction vector when you look at parametric form. It's just the coefficients of the parameter t. So it would just be 1/2, 3, 1. Okay? Now, what if at the beginning of this process, I had chosen to eliminate the y's, or I had chosen to eliminate the z's? Can you see that it's very reasonable that my final answer would have looked very different? But why does that not worry me, that I might have ended up with an answer that looks very different if I start with a different elimination? Why is that not such a big worry? What can we say about the vector equation or parametric equation of a line? No? That's it. This is not unique, okay? There's infinitely many ways to write the equation of a line. Now, say, you know, student A did it this way and student B did it another way. What would be one quick thing you can do to check that you likely have the same answer? What is something that we know for sure will be similar when it comes to two equations of the same line? What would be a really easy way to check? You could, even less work. There you go. Is look at your direction vectors. If your direction vectors come out to be parallel, chances are you both got the right answer. You know, it would be a pretty fluky thing if you both came out to direction vectors that were parallel and that your point was wrong. Okay, it's not foolproof. If you wanted to check for sure, you'd also check a point. But that's kind of an easy way, or even in the back of the book, it's an easy way to check, you know what, our direction vectors are parallel. Yeah, I probably got the right answer. Okay, so let's recap what your algorithm should be. So your algorithm should always start with check the two normal vectors. If they're parallel, then you check the d values if they're offset by the same scalar multiple, okay, to determine whether they're parallel and distinct or parallel and coincident. If they're not parallel, step 1, eliminate one of your components. Step 2, write one component in terms of the other. Step 3, plug it back into the equation and write the other component in terms of the same variable. Okay, this is important. You want to write it in terms of the same variable. And step 3, let that variable represent your parameter t. And then write out your equation. Okay? So again, this really is an algorithmic process. All right? So any questions on this before we move on? We've got a couple of more examples, and then we might even finish a bit early today. No? Okay. So let's take a look at question B here. All right. So which variable do you want to eliminate in this one here? Take your pick. Who wants to give me a suggestion as to which variable to eliminate? Yeah, Ali, unfortunately, you got fished in on that one, okay? Because that's not step 1 of our algorithm. Remember, step 1 of our algorithm is to see that you look at your two, now I'm writing it out here to be really explicit. You don't necessarily have to write it out as much as I am. I look here and I've got a normal vector of 1 for -3, and then I've got my second normal vector is 2, 8, -6. And what I notice here is that n2 is equal to 2 times n1. So in other words, these two planes are parallel. Now, what is it that I have to check to determine parallel and distinct or parallel and coincident? There you go. I check the d value and I look at my d2, okay, is not equal to 2 times d1 because 11 is not equal to 2 times 6. Okay, so since the d values are not offset by the same scalar multiple, okay, there you go, no points of intersection. Okay, and if I want to give a geometric explanation here, planes are parallel and distinct. Okay, now I'm not actually going to do this, but who can kind of give me a sense of what this should look like if I forgot to do this? Because remember, the algebra should always give you the answer. What do you think would happen if I were to try to do elimination here? And think back to what we saw last time with a line and a plane. What should happen if I were to try to do elimination on this here? Yes, and what else would I see? And what can you tell me about those d values? Okay. Yeah, okay, I think I see what you're saying. Essentially, you'd end up with something like 0 equals 4, or 5 equals 7, or -2 equals 18. In other words, you would end up with some equality that was not true. Okay, and so so we saw that last time when we did it with a line and a plane, we kind of did the work and we ended up with 0t equals 8. That's a contradiction. So it means that your original thing that there was any points of intersection must be incorrect. So same thing here. Even if you forgot to do this, no problem. The algebra will show you the way. Okay, you would get something like 0 equals 5. Okay, but always nicer if you can see that before you even start. All right. So this, little bit of a hitch in this one here because that second one is given in vector form. So we're going to have to come up with a way now to solve this intersection with one of them in vector form. Does anybody have any suggestions? How might I deal with this?
Convert the second one to Cartesian form.
Okay, so I've got, looks like two suggestions. So one of them is to write this in parametric form and presumably then put that into the equation. Or the other one is just put this thing into Cartesian form and solve that way. And that's actually what I'm just going to suggest we do, is just take this. It's so quick. I mean, once you get quick at putting this into Cartesian form, that's going to be my suggestion, is let's just put this in Cartesian form and then we can solve using our, very easy algorithm. Okay. So why don't I give you a couple of minutes to work on this one here. So again, I suggest you take this plane, convert it into Cartesian form, and then solve as usual. So I'll give you maybe, I don't know, five minutes to work on this. Okay, so we're back. So let's just go through the solution quickly and check that you got the right answer. And again, your answer might look a little different, but I would say if your direction vector is parallel to mine, then you probably got the right answer. All right. So let's try to go quickly here. Step one, I want to turn this into Cartesian form. What's the first thing I do? Okay, at this point, there should be, there you go, find n, take the cross product of the two direction vectors. So 1, 1, 2, and 1, -1, 3. And again, check my algebra, please. So here we got 3 minus -2. 3 plus 2 is 5. Here we've got 2 minus 3, -1. And then here we have -1 minus 1, -2. Okay, and then from there, I'm going to stick my point into Cartesian form and determine the d value. Okay, so here we have 5 times 2 minus 1 times 3 minus 2 times 1. Now, one thing I'm noticing here is, notice in this equation, the d value is on the other side of the equation. Okay, perfectly valid. There's nothing wrong with that. So what I'm going to do is I'm just going to do essentially the same thing in this vector equation, in this Cartesian equation, just to keep it consistent with this one. Or I could bring the 5 to the other side. Either way, doesn't matter. So what I'll do is I'm going to put that d value on the other side, and let's see what we get. We get 10 minus 3, 7 minus 2 is 5. Okay, so now I have my two equations, x plus 2y minus z equals 5. And then here we have 5x minus y minus 2z equals 5. Okay, so this is the system that I'm going to be solving. Okay, so I'm going to choose to eliminate, I'll eliminate the z's, although the y's would have also been good. I probably would have avoided the x's here. Y multiplied by something so big. So I'll do 2 times 1. So what do we have? We have 2x plus 4y minus 2z equals 10. And then equation 2, 5x minus y minus 2z equals 5. And I'm going to subtract these. Okay, 2 minus 5, negative 3x. Okay, 4 plus 1 is 5, plus 5y. These cancel out. 10 minus 5 is 5. And I'm left with an equation in x and y. Okay, I'm going to solve for y just so that I have only one fraction instead of 2 because of this 5 here. Otherwise, there's no way to completely eliminate any fractions here. So 5y equals 3x plus 5. So y is 3 over 5x plus 1. Okay, now I'm going to take this and input it into one of the equations. I'm going to pick, well, doesn't really matter. I guess equation 1 looks a little nicer. Not that it makes a big difference here. So x plus 2 times y, which is 3 over 5x plus 1, then minus z equals 5. So let's simplify here and let's write z in terms of x. So first of all, bring the z to the other side. Okay, so here what do we have? I have x plus 6 over 5x plus 2 and then minus 5. So z is equal to, so this is 5 over 5x plus 6 over 5x is 11 over 5x. 2 minus 5 is negative 3. Okay, so what have I accomplished? I've written z in terms of x, y in terms of x, so I'm going to let x be my parameter. Oops. Okay, so the equation of my line is given by x equals t, y equals 3 over 5t plus 1, and z is equal to 11 over 5t minus 3, where t can be any real number. Okay, so like I said, the quick way of getting a sense as to whether you have the same answer, if yours looks different than mine, is take a look at the direction vector. So the direction vector here is 1, 3 over 5, 11 over 5. Okay, do you have a direction vector that is parallel to this one? If it is, then you almost certainly have the correct answer. Okay, if it's not, then one of us made a mistake somewhere. All right. So what we now have is we have ways to find intersections of two lines, a line in a plane, and two planes.